Check the convergence, divergence of the following series. You get the series of -3 to power n x to the n divided by square root of n plus 1 and start from 0 and it goes to infinity, everybody. So first of all, what type of series do you have here? This is a power series. Remind yourself of the definition of a power series. A power series centered at the origin is defined as the summation of Cn x to the n and start from 0 to infinity, which is C sub 0, C sub 1x, C sub 2x squared, plus the rest of the terms. To check the convergence of a power series, we use ratio test. The ratio test says if you have a summation like an, when you take the limit of absolute value of an plus 1 over an as n goes to infinity, it must be less than 1, so you have a convergence series. So we're going to use ratio test. Ratio test and power series, they are closely connected. Pay attention here. Your an is equal to this quantity. Everything is assumed to be general term an. So let us take the limit. What is the limit of? On the numerator, we're going to write down an. Let me use a different color for that. So an plus 1 is going to be -3 to power n plus 1, x to power n plus 1, divided by square root of n plus 1 plus 1. And on the denominator, you're going to just copy down your an, which is -3 to power n x to the n divided by square root of n plus 1. You're going to take this limit as n goes to infinity. So let us do a little bit of algebra and simplify this guy as much as we can. By algebra, we're simplifying this limit first, then we take the limit. So here you have the limit of, so let us do the multiplication between the first numerator and the last denominator. So you end up with -3 to power n plus 1, x to power n plus 1 times square root of n plus 1 divided by, you have square root of n plus 2 times -3 to power n times x to the n. But you can simplify this guy further. This is equal to the limit of -3 to power n plus 1 can be written as -3 to power n times -3. X to power n plus 1 can be written as x to the n times x, and you have the square root of n plus 1. Divide everything by the quantity on the denominator, which is square root of n plus 2 times -3 to power n times x to the n. N goes to infinity. So simplify as much as you can. You can cancel out x to the n, x to the n. You can cancel out -3 to the n, -3 to the n, and you are now finding the limit. This can be written as the limit of the absolute value of -3 times square root of n plus 1 divided by square root of n plus 2. Or for now, let us just write this guy down here, divided by square root of n plus 2 multiplied by the absolute value of -3 times x, and then take the limit as n goes to infinity. But pay attention here, on this side, you don't have any n to worry about, so it stays as it is. Or you can write it as absolute value of 3x, which is 3 times absolute value of x. So one by one, First of all, the limit of square root of n+1 divided by square root of n+2 when n goes to infinity, this is just 1. So you have absolute value of negative 3x, and it must be less than 1 using the ratio test. Remember that. Okay, let us continue. So the absolute value of 3x must be less than 1, or 3 times absolute value of x must be less than 1. Divide everything by 3 and find the boundary for your x. So absolute value of x is less than a third, or using algebra, your x is bounded between -3 and 1/3 and -1/3. So by the ratio test, we have the following case. We have the following scenario, right? You can say that, hey, the radius of convergence is a third. Let us call this radius of convergence. Why is that? Because around 0, remember that the center is at 0. Any number between a third and negative a third gives you a convergent series by using the ratio test. But as you remember, the ratio test doesn't tell us anything about the bounds, negative a third and positive a third. And for the radius of convergence, the distance between 0 and each bound is a third. So this is your radius of convergence, a third. So note that the ratio test doesn't give us any information about convergence or divergence of the series at the bounds. What are the bounds? X equals to negative a third and x equals to a third. So we have to do it manually. So we have to check the power series convergence at each bound ourselves. Okay, let us begin. This is our power series, the summation of -3 to power n times x to the n divided by square root of n plus 1. N starts from 0, goes to infinity. At x equals to negative a third, your power series becomes the following series. This series becomes a series of -3 to power n, negative a third to power n, divided by square root of n plus 1, as n starts from 0, goes to infinity. So when x is equal to negative a third, this power series becomes a regular series, everyone. So what happens here? What I have, let us do a little bit of algebra. This guy is equal to the summation of -3 to power n times, here you can write this guy as 1 to the n divided by -3 to the n, and divide everything by square root of n plus 1, n starts from 0, goes to infinity. You can cancel out -3 to the n, -3 to the n. What happens here is that you end up with a series which is comparable to a power series. This is equal to 1 divided by square root of n plus 1, n start from 0 to infinity. But this series is comparable to a p series. Which p series? The summation of 1 divided by square root of n, and start from 1 goes to infinity, or the summation of 1 divided by n to a half, which in this case p is equal to a half, is less than 1, so it is a divergent series. So since this series is divergent, at x equals to -1/3, you end up with a divergent series. So this is your takeaway. Since at x equals to -1/3, our power series becomes a divergent series, so we have to exclude -1/3 from the interval of convergence. So far, we indeed for sure can say that this guy doesn't give us any convergence. Now your goal is to check x equals to 1/3. What happens when you have x equals to 1/3? The same process. At x equals to 1/3, your series, which was the summation of -3 to power n x to the n divided by n, n starts from, this is square root of n plus 1, and from 0 to infinity becomes the following series. This becomes the summation of -3 to power n times 1/3 to power n divided by square root of n plus 1, and start from 0 goes to infinity. So let us do a little bit of algebra and simplify this. This is equal to the summation of -3 to power n times 1 divided by 3 to the n over square root of n plus 1, n start from 0 goes to infinity, which in turns can be written as the summation of -1 to power n, 3 to power n times 1 divided by 3 to the n divided by square root of n plus 1, n start from 0 goes to infinity. So you can cancel out 3 to the n, 3 to the n. This series, as you remember, is an alternating series. So you get the summation of -1 to power n divided by square root of n plus 1, n start from 0, goes to infinity. So again, as you recall, this is an alternating series. For an alternating series, the general behavior of alternating series was -1 to power n minus 1 times bn, and start from 1 goes to infinity, and with two conditions: if bn is decreasing, and if the limit of bn as n goes to infinity is equal to 0, we say that the series is convergent. The series of -1 to power n minus 1 bn, and starts from 1 goes to infinity, is convergent. So this series is very similar to an alternating series, right? So when you have an alternating series, you need to check each one of these one by one. For the first condition, your Bn, which is equal to 1 divided by square root of n plus 1, you can write it as f of x, which is 1 divided by square root of x plus 1. Then you take the derivative of x using the quotient rule. This is 0 times square root of n plus 1 or x plus 1. To be more precise, when we are taking the derivative using f of x, square root of x plus 1, minus, here you have 1 divided by 2 times square root of x plus 1 divided by square root of x plus 1 to the second power, which we can simplify this as -1 divided by 2 times square root of x plus 1 times, here you get x plus 1 back. But the thing is that on the denominator, everything is positive. Given the domain, you have a positive denominator, but on the numerator, it is negative. So this fraction becomes a negative fraction. So f prime of x is negative. What's the meaning of that? So f of x is decreasing, but f of x representing bn, which is 1 over square root of n plus 1, is decreasing. So the first condition is met. Now we move on and check the second condition, which is very easy for you. The limit of bn as n goes to infinity is the limit of 1 divided by square root of n plus 1 as n goes to infinity, which is 0. So the second condition is met. What the meaning of that? It means that you end up with a convergent series. So the power series at x equals to, the x that we were checking was 1 over 3. At 1 over 3 is a convergent series. So what is our takeaway? Our conclusion is, so by ratio test, we saw that the interval of convergence for the series of -3 to power n times x to the n divided by square root of n plus 1 and start from 0 to infinity is open interval -1/3 and 1/3 by using the left and right bound. We saw that at x equals to -1/3, we have a divergent series. At x equals to +1/3, we have a convergent series. So the interval of convergence is half open and half closed interval. Let us recap what we did here. It's a long process. You need to be very patient. We want to check the convergence and divergence of the power series. You have a power series, -3 to power n, x to the n, divided by square root of n plus 1. When you have a power series centered at 0, the power series is defined as the summation of Cn x to the n and start from 0 to infinity. We use a ratio test to analyze the behavior of the power series. Ratio test says, hey, take the limit of the absolute value of the general term an plus 1 divided by an as n goes to infinity. As long as it's less than 1, we have a convergent series. So on the numerator, we have an plus 1. On the denominator, we have an. We do a little bit of algebra to simplify this into the limit of square root of n plus 1 divided by square root of n plus 2 times absolute value of negative 3x. The whole thing must be less than 1. But the limit of square root of n plus 1 divided by square root of n plus 2 is 1. So this guy is just 1. You end up with absolute value of negative 3x, which is nothing but absolute value of 3x less than 1. You can factor out or write down 3 outside the absolute value because it's just a positive number times absolute value of x and set it less than 1. Divide everything by 3. The absolute value of x is less than a third. So x is in between negative a third and a third. So the ratio test gives us the left and right side for our interval of convergence, but it doesn't tell us anything at the point 1/3, 1 divided by 3 and negative 1 divided by 3. For those two bounds, we have to do everything manually. It means that we need to plug in a third, we need to plug in negative a third and check the power series, which becomes a regular series that you saw before. When x is equal to negative a third, your power series becomes a regular series that you already saw. You already know the test for convergence for regular series. When you do a little bit of algebra, this integral becomes the integral of, this series becomes the series of 1 divided by square root of n plus 1. And it's comparable to p series when p is equal to a half. But since this series is divergent, you can conclude that this series 1 divided by square root of n plus 1 also a divergent series. It means that we have to exclude negative a third from the interval of convergence. Now we're going to check the next bound, which is positive a third. At positive a third, your power series becomes a regular series that you saw before. You know how to analyze this. When you do a little bit of algebra, this series becomes an alternating series. For an alternating series, if two conditions are met, you have a convergent series. But we just showed that Bn is decreasing and the limit of Bn goes to 0. So you have a convergent alternating series. It means that this series is convergent. So what's the meaning of that? It means that the power series is convergent at the bound on the right-hand side. So it means that when you're writing the interval of convergence, the interval is half open, half closed interval. Half open, half closed interval. And also we saw that the radius is equal to a third. Perfect.